Hello and welcome to the lecture of challenges in nanotechnology. In this lecture, let us see what are the different challenges in nanotechnology. So, research in the field face many new challenges that are unique to nanostructures and nanomaterials. So, even though the fundamentals are well established in the interdisciplinary fields such as physics, chemistry, material science, and device science and technology, researchers in the field of nanotechnology face many new challenges that are unique to nanostructures and nanomaterials. And the integration of nanostructures and nanomaterials into our microsystems that can interfere with the people. So, this is one challenge. Actually, the building and demonstration of novel tools to study at the nanometer level what is being manifested at the macro level. So we are synthesizing nanomaterials, nanostructures, and nanosystems which are at nanometer level, and their manifestation is at macro level. So building and designing the tools to study that nanometer level systems at the macro level is one major challenge that researchers face. So the small size and complexity of nanoscale structures make the development of new measurement technologies more challenging than ever. Because of the small size and complexity, the measurement is more challenging. So as the complexity of nanostructures increases, then its measurement will also become challenging. So measurements of physical properties of nanomaterials require extremely sensitive instrumentation, while the noise level must be kept low. So yeah, we need sensitive instrumentation as well as the noise level of that instrument should be must be very low. So new measurement techniques need to be developed uh, at the nanometer scale and may require new innovations in metrological technology. So basically, metrological technology is all about measurements. So we need new innovations in the metrological technology to get the right measurement techniques for nanometer scale measurements. So, for example, electrical conductance, electrical capacitance, tensile stress. So these are measured and used to calculate the electrical conductivity, dielectric constant, and tensile strength. So basically, although the material properties such as electrical conductivity, dielectric constant, tensile strength are independent of dimensions and weight of the material. So the electrical conductivity sigma, it is a characteristic feature of the material. It is not going to change by dimensions. Similarly, dielectric constant and tensile strength. But these properties are measured experimentally. So even though these are independent of dimensions and the weight of the material, they are measured experimentally. Like electrical conductance, capacitance, and tensile strengths. These are measured and are used to calculate electrical conductivity, dielectric strength, and tensile strength. So, as the dimensions of materials shrink from centimeter or millimeter scale to nanometer scale, the system properties would change accordingly, and mostly they decrease with the reducing dimensions of the sample material. Now, for example, if we reduce from centimeter to nanometer scale, in that case, the magnitude can decrease in the order of 6 orders. For example, if it is 1 unit, when we reduce from centimeter to nanometer scale, it will be 10 power minus 6. So it would be that small. When we go from centimeter to nanometer scale, the quantities are going to reduce in such a fashion. For example, in centimeter range of a system, for example, we have um, current density of 1 ampere per centimeter square. Now, when we move from centimeter to nanometer scale, or it need not be about current density, but in general, about most quantities, the for example, current density would reduce to 0.00001. That is 10 power minus 6 ampere per um, meter square, which is a very small quantity. So the measurement of that would be very difficult. Another important thing is in case of dope. So we dope semiconductors to get the desired properties of a semiconductor material. In case of nanomaterial semiconductor, the random doping fluctuations can affect have a huge impact on the properties of the material. Uh, so at nanometer scale, we cannot accept the fluctuation of doping concentration. So we need a uniform doping concentration in the material. Suppose if we take a doping concentration of 10 power 18 per centimeter cube, which is a typical uh, in a typical material, uh, so the typical doping concentration in a semiconductor, for example, 10 power 18 per centimeter cube. Now, suppose consider a nanomaterial of a cube having side 10 nanometer, each side having 10 nanometer. So if we take such a nanomaterial cube and for a doping concentration of 10 power 18 per centimeter cube, there will be only one atom in that cube. So then it is so the distribution fluctuation of dopants will result in a total different functionality of device in a such a size range. Now, so it becomes even more complicated with the location of the dopant atom. So in this case, when we consider 10 nanometer cube, there is only one dopant atom. So the location of that atom also affects the properties. Like a surface, suppose if the atom is present at the surface, then it would behave differently compared to uh, an atom in the center. So in this case, the challenge will be not only to achieve reproducible and uniform distribution of dopant atoms in the nanometer scale, but also to precisely control the location of dopant atom, because the location of the dopant atom also will affect the properties. So to meet such a challenge, the ability to monitor and manipulate the material processing in the atomic level is crucial. Uh, so that is a challenge when in the case of doping nano semiconductors. And also doping itself imposes another challenge in nanotechnology, since because of the self purification of nanomaterials, it makes doping very difficult. For the fabrication and processing of nanomaterials and nanostructures, the following challenges must be um, met. First thing is that overcome the huge surface energy, because nanomaterials are very small, have more surface atoms. Surface atoms the ratio of surface atoms to the total number of atoms of nanomaterials is higher compared to bulk materials. Hence, there will be more surface energy, and this surface energy has to be uh, overcome to fabricate and processing of nanomaterial and nanostructures. And the secondly, ensure all nanomaterials with desired size. So when we are to achieve the desired physical properties, then we need to fulfill all these constraints must be satisfied. That is achieving the desired size, uniform size distribution, morphology, crystallinity, chemical composition, microstructure. So when if we achieve all these, then only we can obtain desired physical properties from the nanomaterial. And also, these the another challenge is the prevention of coarsening the material through either asphalt ripening or agglomeration as time evolutes. So these nanoparticles should exist independent or separate. There should not be agglomeration of the nanoparticles. So this is another challenge that has to be met for the fabrication and processing of nanomaterials and nanostructures. So these are the challenges in nanotechnology. Thank you so much for watching this video, and please subscribe to get more videos.